Thank you very much. Good afternoon, everyone. My name is Yukio Nozaki from Keio University, Japan. First of all, I'd like to thank the organizers for inviting me and giving an opportunity to present our recent work. Today, I'll be talking about our experimental study on alternating spin current generation in copper thin film by injecting surface acoustic waves. This is a collaborative work by Keio University. This is my student and Professor Saito's group of Tohoku University and Professor Maekawa of Japan Atomic Energy Agency. Now, all of experiments were conducted by this my student Kobayashi-kun and Kurimune-kun, and other persons mainly supports the theoretical and numerical parts. This is an outline of my talk. First, I will briefly introduce you what is spin vorticity coupling. That is, vorticity means local rotation. So this one is almost same as a spin rotation coupling, which is an inertial effect on electrons in a rotating metallic body. Then I'm going to talk about how to generate a spin current by this spin vorticity coupling using a surface acoustic wave. After that, I will share with you some of the experimental results that shows an evidence of successful generation of alternating spin current by spin vorticity coupling using a surface acoustic wave in copper film. Now, finally, I will make a brief summary of this talk. As schematically shown in this figure, the spin current is a flow of spin angular momentum caused by a non-equilibrium spin state. Such a spin current has been widely used to control various spintronics devices such as spin random access memory or spin torque oscillators. And non-equilibrium spin state needed for generate a spin current can be realized by using spin accumulation at the interface between the ferromagnet and the non-magnetic materials, thermal gradient in ferromagnet, phonon or magnon dynamics. Moreover, the momentum rocking and spins caused by spin orbital interaction can be also generate a spin current. However, all of these methods need ferromagnet and or novel non-magnetic materials with a strong SOI. SOI means a spin orbital interaction. Recently, an alternative method to generate a spin current in familiar non-magnetic materials with weak SOI has been theoretically proposed by Professor Matsuo and his collaborators. The method is based on the interaction between the microscopic spin angular momentum and the macroscopic rotational motion of the body. It is widely understood that the spin angular momentum can be mutually converted using this macroscopic rotation in accordance with the law of angular momentum conservation. Indeed, the conversion from the magnetic moment originated in the spin angular momentum to the macroscopic rotation was experimentally demonstrated by Einstein and de Haas, while the Barnett produces the inverse effect. The Professor Matsuo predicted that the same kind of mutual conversion can be realized for free electrons in non-magnetic materials. That is, this spin rotation coupling can lead to the spin accumulation, not the magnetization, originated from the spin angular momentum of conduction electrons. It is noted that such a spin rotation coupling is a consequence of an inertial effect appeared when a local inertial frame accelerates and rotates. This phenomena is defined by this Hamiltonian here, and here is sigma is the vector of Pauli matrices, and large omega is angular velocity of mechanical rotation given by the half of rotation of velocity field. As you can see here, the omega can be coupled with sigma, similarly to the magnetic field in the Zeeman effect. And the amplitude of this equivalent magnetic field, called as a Bannet field, is given by omega over gamma. Gamma is gyromagnetic ratio. Such a Bannet field, recently, such a Bannet field was successfully observed and solid by nuclear magnetic resonance. Dr. Chudo and Dr. Ono of Eiji Saito's group demonstrated the generation of spin rotation coupling derived Bannet field and both nuclear spin system and rare earth materials in paramagnetic states using this rotor, which frequency of up to 10 kHz. And they used the large rest mass here in an atomic nucleus, which leads to a large Bannet field. The figure on your left-hand side shows NMR spectra measured at various angular velocity for 115 indium and 29 silicon, which have positive and negative G factors. As you can see here, they successfully observed the linear variation of frequency shift in NMR spectra with respect to the omega. And they concluded that Bannet fields successfully observed because this shift depends on both the sign of omega and Z factor, that is gamma. And moreover, the same group demonstrated the spin current generation using vorticity in mercury flow. The detail has been already explained by Professor Saito Sensei on the first day of this conference, so I'll skip this one. And according to the theory, higher frequency is preferred to generate a larger spin current. But in these experiments using mercury flow or high-speed rotor, it is hard to increase the frequency of mechanical rotation to the order of gigahertz. To overcome this difficulty, Matsuo Sensei proposed the alternative method to generate a spin current using a surface acoustic wave. As shown in this animation, in elastic material, a lattice deformation can propagate along its surface, this one. In this Rayleigh-type surface acoustic wave, the particle motion consists of elliptical motion, this one, and the vertical plane, and parallel to the direction of propagation. And important is that this frequency can be increased up to gigahertz. This figure shows the velocity field of displacement vector of the lattice in the Rayleigh-type surface acoustic wave. As you can see here, the amplitude of velocity field decreases in depth with decay length approximately as long as wavelength of surface acoustic wave. This figure shows the temporal evolution of the vorticity of this Rayleigh-type surface acoustic wave. And here is the depth direction, and this direction is surface direction. As you can see here, this lattice deformation can generate a gradient of omega, that is a Bannet field, along the depth direction. Similar to the Stern-Gerlach experiment, the field gradient leads to an opposite flow of up and down spin. However, here it should be noted that the spin rotation coupling directly converts the omega to the electron spin in non-magnet, so that the vorticity gradient, this one, produces a gradient of spin accumulation, then which leads to an opposite flow of up and down spins. Anyway, by using this method, the spin current can be generated without using a ferromagnet nor high spin orbital interaction materials. Here it should be noticed that, as shown in this figure, the sign of gradient of magnetic field is periodically changed both spatially and temporally. Namely, the amplitude of the consequent spin current is temporarily varying, that is AC, and periodically distributed on the plane. These these phenomena make it difficult to detect the spin current using an inverse spin Hall effect because the Hall voltage caused by such a periodically distributed spin current is compensated. So, uh, yes, yes, that's excuse me. Spin orbital interaction is not. Yeah, as as you said, yes, lattice and electron is coupled by somewhat. For example, spin rotation, spin orbital interaction. But but mm, and this is inertial effect. So we need electrons should be confined in this material in order to realize inertial effect. Mm, it's yeah. Hmm? But I think it is difficult to answer. uh, anyway, we can make the spin current in copper. So I think I believe the spin orbital coupling is not important for this phenomenon. But electrons should be confined in this material, and something interaction with lattice is needed to feel the inertial effect. Yes, that's right. I'll show it later. Yes, yes, that's right. Yeah. That anyway, continue to explain. Yeah, in order to confirm the spin current generation via spin vortice decoupling, we prepared a bilayer consisting of non-magnetic and a ferromagnetic layer, which act as a spin current generator and a spin transfer torque detector. When the surface acoustic wave propagates as the bilayer system, the spin current is generated in copper and is diffused toward the ferromagnet. This spin current applied spin torque to magnetization. When the external magnetic field is matched with this ferromagnetic resonant field at the frequency of this alternative spin current, and FMR is excited and energy dissipation occurs in this ferromagnet. Important is that this energy dissipation is in proportion to the square of spin current. So we can measure this microwave absorption owing to up and down spin without compensation. And this change in energy dissipation leads to the suppression of surface acoustic wave amplitude, and this one can be easily measured using a vector network analyzer. You said this have a spin orbital interaction and effect on the copper. Only nickel iron. We did the experiment. Copper permalloy bilayer, permalloy only, copper silicon dioxide permalloy, and titanium permalloy or titanium nickel copper alloy. Yes. 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 This one shows photograph of device and schematic experimental setup. The two interdigital transducer, which produces a periodic electric field, was prepared on the lithium niobate substrate. And then the rectangle of ferromagnetic and non-magnetic bilayer consisting of these materials was prepared between these IDTs. And in this study, we compare highly conductive copper and poorly conductive titanium as the spin current generator, because the theory predicts that higher electric conductivity is preferred to generate a higher spin current. And amplitude of propagating surface acoustic wave was measured using a vector network analyzer at the given DC magnetic field at the angle from the propagation direction. This field was applied to match the ephemeral frequency of this ferromagnet with exciting frequency of Rayleigh-type surface acoustic wave. The wavelength of surface acoustic wave can be changed by varying the finger width of these IDTs. And by changing, in the case of Rayleigh-type surface acoustic wave, it is known that the propagation velocity is almost independent of its wavelength. So we can change the frequency by changing the finger width. And in this device, we can change the frequency in the range from 1.4 to 1.9 gigahertz by decreasing the finger width from 700 to 500 nanometer. And this one is the main result. This one shows reduced microwave absorption measured for permalloy copper bilayer as a function of frequency and external magnetic field at 0 degree. The white curve represents the condition for exciting FMR, while the dotted line shows the exciting frequency of surface acoustic wave. As you can see here, a large microwave absorption can be observed when the external magnetic field is consistent with the resonant field at the exciting frequency of Rayleigh-type surface acoustic wave. Yes, this frequency means, yes. Omega, yes.
Is proportional to the square of the frequency of the surface acoustic wave and the first power of the amplitude of the surface acoustic wave.
That's right. But this frequency is not omega frequency. This one is the input frequency of the
But you're not saying anything about the
and
amplitude.
we confirmed that in this frequency, the amplitude of surface acoustic wave becomes maximum.
But
Here,
how big is it?
this one is amplitude of propagating surface acoustic wave as a function of input frequency. This peak shows clear evidence propagating the surface acoustic wave.
This is the transmitted signal?
Yes, transmit signals.
But if you have amplitude less than 0.1 nanometer, then your omega will be very small to generate any effective magnetic field that will produce any visible effect. So what is very important here is the amplitude of surface acoustic waves. You have to generate very large amplitude of the surface acoustic waves in the gigahertz range.
Mm.
Absolutely right, but he is not discussing that. He's simply saying that the effect takes place
Mm.
only at the magnetoacoustic resonance. That's all.
Well, but this is my question because I don't see how the effect may appear there if there is not a very high amplitude of the surface acoustic waves, which is extremely difficult to generate.
The vorticity is modulated at the frequency of the waves. So then it's just a resonant effect. The amplitude might be small.
Mm.
Whatever it is, just
Q, there is Q, the Q factor of the resonance.
No, but the effective field you're generating like orders of magnitude less than the Earth.
I propose that we let the speaker finish the talk.
It is difficult to answer. Yeah, no. Yes, as you said, the amplitude of surface acoustic wave is very small. So the effective field is also very small. But important is the gradient of the Bannet field to generate the spin current. Yes. And this seems to show. This seems to be no. This result shows that our assumption that spin current is successfully generated in spin copper. No. Excuse me. It's and, and this result seems to prove our assumption, but the spin torque on the magnetization is also produced by the magnet striction effect in a ferromagnet and or electromagnetic field leakage from the interdigital transducer. Moreover, spin vorticity coupling in ferromagnet produces a Bannet field in this ferromagnet. This also apply the magnetic torque. So in order to confirm the successful generation of AC spin current in non-magnetic film, we need to evaluate another effect. Now first, we examined which is important, magnet spin surface acoustic wave or electromagnetic field from the interdigital transducers. The most important difference is the wavelength between the surface acoustic wave and electromagnetic field. The wavelength of surface acoustic wave in this device is much shorter than the size of bilayer. So the this surface acoustic wave will excite a spin wave whose k vector is consistent with the surface acoustic wave. On the contrary, in the case of electromagnetic field, the wavelength is much longer than the bilayer. So the electromagnetic field will excite a uniform mode. And in the case of spin wave mode, the resonant frequency depends on the angle between the magnetization and the k vector, while the uniform mode, the resonant frequency is almost independent of the angle if the in-plane anisotropy is negligibly small. And this result shows microwave color plot of microwave absorption as a function of angle and amplitude of external magnetic field measured for palm alloy copper bilayer and palm alloy nickel and copper bilayer. This one has different saturation magnetization, so the resonant condition for spin wave is different. The solid curve and the dashed line represents the resonant condition for spin wave mode. And as you can see here, the strong absorption appeared when the spin wave is excited. So from this result, we can exclude the influence of the electromagnetic field from the interdigital transducers. And moreover, from the angular dependence of the amplitude of microwave absorption, we can evaluate the influence of magnet striction effect. The spin transfer torque will be at maximum when the spin angular momentum of spin current is orthogonal to the magnetization. Conversely, the collinear orientation of injected spin with magnetization will completely eliminate the spin transfer torque. In the case of spin current generated by spin vortex decoupling, the spin angular momentum rise in plane and perpendicular to the surface acoustic wave propagating direction. So by changing the angle between the magnetization and the k vector of surface acoustic wave, we can change the spin transfer torque. And as you can see here, the strongest microwave absorption was observed at theta equals 0, where the maximum spin transfer torque is expected. On the contrary, in the case of magnetostriction dominant case, the maximum absorption appeared not 0 degree at 25 degree. This result is measured for nickel copper film alone, which shows a magnetostriction effect. The same kind of result was observed by Dr. Weiler and the collaborators. They concluded that owing to the coexistence of normal strain and shear strain, maximum amplitude or microwave absorption appeared at angle between 0 to 45 degrees. So this result showing the maximum maximum absorption at 0 degree shows clear evidence we observed the spin transfer torque arising from the spin current generated by the spin vortex decoupling. And next, we compare the absorption owing to spin transfer torque and Barnett field torque. And important is that from the power loss formula, we can expect that the power loss due to the spin transfer torque is roughly inversely proportional to the saturation magnetization, while that of Barnett field is in proportion to saturation magnetization. So from the saturation magnetization dependence of the power loss, we can examine which is main contributor. And this one is shows a result of comparison. Green one shows the nickel copper alloy and copper bilayer, and blue one is palm alloy copper bilayer. And nickel copper bilayer saturation magnetization of nickel copper bilayer is 1/3 of the palm alloy. Now, as you can see here, decrease in the saturation magnetization leads to markedly increase of microwave absorption. So from this result, spin transfer torque from spin current generation, spin current generated by spin vortex coupling is much stronger than the torque owing to the Barnett field. Indeed, microwave absorption can be suppressed, strongly suppressed by inserting the thin insulating silicon dioxide or removing the copper, this one, these results qualitatively shows the spin current is generated in a copper and injected to the permalloy film. Now finally, I think time is over. Okay. Finally, quickly, I will discuss about the origin of spin current by spin vortex decoupling. From the theory described in this paper, there is two processes generating the spin current. One is the spin-dependent force field due to the spin vortex decoupling. That is the Stringer-Harlike effect. And another is the additional spin flip relaxation process driven by the spin vortex decoupling. And this equation shows the analytical expression of spin current. And the first term is this owing to this process, and the second term is this one. Then tau SF means the spin flip time, and the theta is normalization factor representing the conversion efficiency from the spin and mechanical rotation. And this one is the complicated equation showing the reduced microwave absorption derived by considering the two processes of spin current generation and the Barnett field. And we found that each contribution shows a different power law with respect to the frequency. And this one shows the frequency dependence of microwave absorption for copper permalloy bilayer and the titanium permalloy bilayer. As you can see here, the copper bilayer shows strong microwave absorption than the titanium, and we can increase the microwave absorption, that is the spin current, can be increased with increasing the frequency. Now from the curve fitting with this equation, we can evaluate the first, second, and third term, that is first, second, third term. And we found the second term is much larger than the another part. And these results shows that theta in our case is much larger than tau SF omega. This situation is almost same as the spin current generation using vorticity in liquid mercury experiment done by Professor Saido's group. And furthermore, the ratio between the second term between copper and the titanium, this one is 245, and the square root of this value is almost same as the ratio between the electrical conductance between copper and the titanium. This result clearly shows that the strength of the spin current generated by surface acoustic wave is in proportion to the electrical conductance. So this is a summary. Thank you very much. Yeah. Yes.
One for the experimentalists.
Yeah.
Do you have a homogeneous mode excited with constant phase in the layer, or is the phase changing because of the surface acoustic waves?
Homogeneous wave
Is
means
it really homogeneous precession, or does the
in
phase change over the layer?
we believe that the spin wave is excited.
But then you also, I mean, you have some spin bumping into the copper. You also have the AC spin Hall effect, and that means that in principle you can leak from one point to the other. And this might explain why the copper, which is highly conducting, gives you additional damping.
One more question while the next speaker.
Sorry, I will discuss later. I cannot.
Well, if you return to that slide that shows the amplitude of the Barnett field, amplitude, yeah, please return to the slide
two slide
amplitude
before.
of the
So,
bar
so, so.
net field.
Okay, okay.
The other one. Yeah, go back one more slide.
Yes.
One more slide back. No, one more.
One more.
Yeah, here.
Yes.
Bar net field.
Yes.
So as I said before, it is proportional to the square of the frequency and
Uh-huh.
the first power of the amplitude of surface acoustic waves.
Hmm.
Now, once you know the amplitude of the bar net field, the problem is totally reduced to the problem of the AC field,
Uh-huh.
AC magnetic field of that amplitude applied to your metal.
Uh-huh.
Now, we know that all the resonant effects that you talked about require a certain amplitude of the AC magnetic field. They will not be seen if the amplitude of the AC magnetic field is below that critical. So the only thing you need is to compare that amplitude of the effective AC magnetic field with the amplitude of the AC field that is going to produce any effect. And it is proportional to the amplitude of the surface acoustic waves. And I have not seen that estimate in your talk. What is that amplitude of the bar net field? What is it? 10 to minus 6 Gauss, 10 to minus 10 Gauss? What is it? If it is 10 to minus 10 Gauss, you will not see any effect of the ones that you studied. And I want to make another very short comment about spin orbit interaction. Here in this room and everywhere on Earth, every spin is subjected to the magnetic field, effective magnetic field, just due to the rotation of the Earth. It's the angular velocity of rotation divided by gyromagnetic ratio. You don't need to know the explicit form of the spin orbit interaction. It is a Larmor theorem of electricity and magnetism. And in that sense, the surface acoustic wave does exactly the same. It locally rotates the solid. But of course, the angular velocity there is much greater than the angular velocity of the Earth. But we don't need to know the explicit form of spin orbit interaction.
Oh, without spin orbit interaction, it will not induce spin imbalance. That's it.
But here on Earth,
If you wait
it
forever,
does,
of
because
course,
every
eventually.
spin is subjected by the effective magnetic field due to
Yes,
the
but
rotation.
that field itself will not induce spin density unless you have spin orbit interaction.
You don't need to know explicit form of that interaction. The effective magnetic field acting on each spin in this room is angular velocity of Earth, 1 revolution per day, divided by the
That
gyromagnetic
field commutes with spin.
Okay, gentlemen,
Yeah.
we're going to thank the person up here.
Thank you very much. Thank you very much. Thank you very much.